we were doing 1302 deepest leaves sum. It's a medium problem, and you're given the root of a binary tree, and then you got to return the sum of its values of its deepest leaves. So you got the deepest leaves being 7 and 8 right here. You got to return the sum of those, which would be 15. In this example 2, you can't see it here, but if you go to test case and you go to example 2, you can see the deepest leaves are 9, 1, 4, and 5, which will all add up to 19. So, um, that's basically the problem.
Yes. Just to understand a little bit. So what a leaf is the last node of the what's it called? The last node of a path, right? Which is usually found on the last level of a binary tree. And these leaves usually are represented by they're the last few nodes of the tree, and they don't have left or right childs, right? So for example, in this case, on example one, by giving by visual, the leaves would be 7 and 8. But yeah, pretty much for it to that's the kind of the only thing that where it's needed to solve this problem.
Yeah, so the initial approaches that like sort of went through my mind were like, okay, if we want to get the deepest leaves, you got two algorithms when it comes to trees, two main ones that I remember, which were BFS and DFS. BFS is breadth first search, and if we go to the skeleton draw, you get to see that it's basically layered searching. So BFS, you start off like with a layer, another layer, another layer, and then another layer, right? If you were to erase all this, let me see, that's locked. If you're to erase it, DFS is just going down one side, and then you go and like there's a couple of them. There's like post order, pre order, in order, right? But basically, you're going all the way down, and then you go and check these, and you got to go all the way down here, and so you're not really getting a level based searching, right? So that's why BFS was the most the initial approach with it.
Yes, so like Carlos was doing a breadth first search, that was the approach we decided to go. And in order to implement this breadth first search, we decided to use queues, right? So a queue is a simple data structure, first in, first out, I believe, if I'm not mistaken. So we decided to use a queue to just hold the to have an organization of all of the nodes and to make sure we're traversing through all the nodes in an order from root, left, and right. So while there's still something in the queue, we want to get the length, right? And we're gonna have another array in order to store the values of the current level we're in. And based on the length of the current length of the queue, which at first is gonna be just a root, so it's just gonna be one. We're not gonna get the actual node, right? And then we're gonna check if the node exists. If the node exists, we're gonna append the value to the level that we're currently in, and then we're gonna append the left and right child to the queue. Again, this queue is gonna help us stay organized and traverse the other nodes in a fashion of the root, then left child and right child. And then afterwards, we're gonna continue on. Afterwards, after we have finished traversing that node, right? We're gonna append that level to the res. Res is just another data structure established over here that is gonna, is just a result. It's gonna store all the different levels, and we're gonna continue doing all of these, all of the traverse until we run out of nodes to traverse. At the end, we're gonna have a data structure. Res is gonna have um, more arrays, which each array represents a different level, and each level with its own nodes and values. At the end, we're going to return the sum of the last level, right? Found in res, which will include the leaf nodes 7 and 8. And after that, we're going to return it, and As a result, you get the right answer. And some key takeaways from this is that my initial thoughts were that I forgot about breadth research and how to implement it. But breadth research, knowing how queues work and how to take advantage of the queues and their own nature, will help you really be able to implement this breadth research.
Nice. My key takeaway was I forgot that, or actually, I didn't know that if you append, do you mind unhighlighting?
Oh, yes, sorry about that.
I didn't know that if that right here in this logic, you could append a node that's not there. So, for example, if you're at node 3, right, and this logic says if node, which will pass because you're at node 3, now you're going to level.append node.val. So level is going to have 3 added to it, the value of 3. And then Q is going to get appended with node.left. But 3 doesn't have a node.left, right? So my initial thoughts were like, that's going to return an error because there's no node you can't append to it, right? But something that I just learned was that it will still append a null value. So it will literally append null to that array rather than give you an error. So what I was going to do to mitigate that potential error was I was going to do if node.left, then you append, and then of course if node.right, then you could append, right? But since that wasn't needed because the dot append, I guess it could append a null to it. So that was my initial key takeaways. But of course, if you see a problem with a tree, sort of, and it wants a sum of stuff, sort of think of those algorithms like BFS, DFS. Those could possibly be like the right approaches to take. And yeah, that's about it. Nice, Jose.